Hey everybody, we are back with more Organic Chemistry 1 study session. We've got some more office hours with you. I'm coming to you live with Chegg. Once again, we are doing these every Tuesday at 5 p.m. Pacific time. Please check out the QR code on the top left of the screen if you want to see what other subjects Chegg is covering. With different office hours, you can get help with math and all the other classes you're taking this semester. Over here, once again, we're doing Organic Chemistry 1 review. I've got some questions that I have that I'm going to review for you. But as always, feel free to chime in. I'm taking questions in the live chat. So definitely keep it Organic Chemistry 1 related. But feel free to ask questions about the problems that I'm going over or something unrelated. If it's something that I can answer pretty quickly without having any kind of materials to reference, I will gladly answer any and all of your organic chemistry related questions. So let's go ahead and get started. Remember last time we started doing a lot of spectroscopy stuff, because definitely a lot of students tend to get confused, certainly with IR, mass spec, that kind of stuff, but definitely NMR. So I wanted to make sure we covered the basics of all those spectroscopic techniques. So let's go ahead and start with one question on IR. So identify the compound that matches this IR spectrum. So when we're looking at Organic Chemistry 1 level knowledge of IR spectroscopy, there's only a few things that you need to be able to do. So what's going on here is infrared light is interacting with the different kinds of covalent bonds in a compound. And so, and if they are being absorbed by a particular type of bond, they don't reach the detector. So this information is telling you what types of bonds are in the compound, whether it's CC, CH, OH, CO, right? All those. The information that shows up with respect to those bonds have a distinct shape and a distinct wave number. So they show up at a particular position on this horizontal axis, right? There's a characteristic place on this axis where that functional group will show up. And then also some of them have a very distinct shape. One or two in particular are the most obviously recognizable resonances on an IR spectrum. So let's go over what they are. Here, we want to understand if this spectrum is isobutene, 3-heptanone, diethyl ether, or 2-butanol. So let's just draw them. Isobutene looks like this, right? It's like isobutane, but it's isobutene. We actually don't have to specify where it is because the double bond anywhere will be the same molecule. So that's isobutene. How about 3-heptanone? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So that's a 7 carbon chain with the carbonyl on carbon 3. Diethyl ether, of course, just looks like that. And then 2-butanol will look like that. So we have a few different functional groups here. We've got alkene, we've got ketone, we've got ether, we've got alcohol. So what is the information that we want to glean here? So the first thing we need to understand is that this region over here is called the fingerprint region. It's a little bit more difficult to parse information out of this region. You certainly can, and in upper level chemistry courses, you do start to learn how to get information from the fingerprint region. When you are first looking at IR spectroscopy, though, it's really this stuff over here that is going to give you the information that you need. So what is the first one that we're very obviously going to need to know? This one here, we've got a very broad, round, smooth peak at right around this wave number here. So that's about 3,300, 3,400, 3,350, somewhere around there. This is where we have this, and this is an OH stretch. So OH meaning it's the light is interacting with an oxygen-hydrogen covalent bond, and it is causing it to stretch. Right, you've got the two atoms here, and they're actually the internuclear distance is shifting. It's stretching and contracting due to being excited by that infrared light. And so, yeah, OH stretch. That's what that is, and you just can't miss it. It's really the most recognizable peak on an IR spectrum because of how rounded it is. It goes all the way down here, very smooth and very wide. Okay, so that's an OH stretch. The other one we want to know about is right here. Let me do that in red. And this is a saturated CH stretch. So CH stretch, same as the OH stretch, it's just CH bonds that are stretching. And saturated means that the carbons that bear those hydrogens are fully saturated. They're not participating in any pi bonds. So basically, it's just alkyl, right? There's alkyl content on the molecule. So those are the two things that we have to work with here. So let's look at these molecules. Well, we need an OH stretch. So that already is going to give it away. Really, this question is very easy because it's just asking if you can recognize the OH stretch. If you recognize the OH stretch, you know that it is going to be 2-butanol, right? This is the only one that has a hydroxyl group. So that's it. Now, a couple of other things that I want to talk about here. The first one being that the carbonyl stretch. So this C double bond O also is going to stretch when irradiated with light of a very particular frequency, and that gives a very distinct resonance as well. And that's going to be, it's right around here. I forget the exact wave number, but the CO stretch would show up here, and we don't see it. There's no data right there, which means there's no carbonyl. So there's no carbonyl in the compound in question. The other thing that I want to talk about is that some students, the main confusion that I see upon first being introduced to IR spectrum is IR spectroscopy is they will identify something like a saturated CH stretch, and they will say, okay, saturated CH stretch, that means it's an alkane, and then they'll try to look for an option that is an alkane and say that's it, and then they'll ignore all of the other data. So that's not what's going on, right? This compound 2-butanol has a saturated CH stretch because it has saturated CH bonds, right? It has there is OH, there's OH there, and then there's H there, and then there's 3 H's here, and there's 2 H's here, and there's 3 hydrogens here, right? So these are all saturated CH stretches. Those are bonds that are present in the compound. The hydroxyl group is also present in the compound, so that will give its own data. So you get data for all of the different functional groups that are in there. So as you can imagine, if you have a compound with many, many, many functional groups, the IR spectrum starts to look very messy because there's a lot of data. There's a lot of different kinds of bonds. The simplest IR spectra are the ones that have very few functional groups, very few different kinds of covalent bonds that are going to be interacting with light in different ways. Right? That's what spectroscopy is. It's the study of the interaction of light and matter. We irradiate compounds with light of a particular type, particular frequency, and then we see what kind of data we can get on the other side based on what light it absorbs. So IR spectroscopy, NMR spectroscopy, they're all doing something like this. So all you're doing, once again, you're just identifying the types of functional groups that must be in the compound by virtue of what kind of data is on the spectrum. OH stretch, there's got to be an OH in there. Saturated CH stretch, there must be saturated CH bonds, right? And so a compound can have multiple functional groups, so you will see multiple resonances on there. So IR is nowhere near as good as NMR in terms of identifying the precise structure. It's really more about just identifying which functional groups are present or not present, right? No CO stretch, no carbonyl. But it's very, very difficult to assign the precise molecular structure of a compound from an IR spectrum. It's not really something that we do. It's an older spectroscopic technique. It's for characterization. If you're doing a Grignard, and you know that Grignards make alcohols, and you get a product and you do an IR spectrum of your product and you don't see an OH stretch, then you know something went wrong because you were supposed to generate an alcohol, and an alcohol would give an OH stretch. So this one's pretty straightforward, but it's just an introduction to the various functional groups, the various types of data that we're looking for. 2-butanol, that's that one. Okay, let me see if I missed anything. Okay, nothing yet. USA says Feynman's technique of integration. I'm not sure if you're talking about something relating to integration on an NMR spectrum, and I just haven't heard of that, or if you're talking about math. If you're talking about calculus, then we will not talk about that. We're doing organic chemistry here. Let's see. Yeah, okay, so that's it for now. We'll come back to more spectroscopy in a little bit. Okay, so here's something else that's important. Last time we were doing a lot of electrophilic aromatic substitution. We're going to do some more of that today too. But in terms of aromaticity, we have to be able to identify compounds as being aromatic, anti-aromatic, or non-aromatic. So what are the criteria for being aromatic? To be aromatic, something has to be cyclic, first of all. Linear molecules cannot be aromatic. Has to be cyclic. It has to be fully planar, right? It has to be a flat molecule, right? Or at least the portion that's aromatic has to be completely flat. It has to be fully conjugated. So it has to have pi electron density, right? Aromaticity is about a delocalization of pi electron density. So we're talking about a combination of pi bonds and lone pairs. Those qualify as pi electrons, and they must be fully conjugated all the way around the ring. There cannot be any portion of the ring upon which the pi electron density does not go. Right, there cannot be any part of the ring that is isolated from the conjugation, from the pi electron density. And then lastly, it has to satisfy Huckel's rule. And Huckel's rule states that the number of pi electrons that are conjugated, that are potentially generating aromaticity, must satisfy 4n plus 2. It must be an amount of electrons that satisfies 4n plus 2, where n is any integer. So if n is 0, we would get 2. If n, let me write that better. If n is 1, we would get 6. If n is 2, we would get 10, 14, 18, etc. And you can have very, very large aromatic systems this way. They're usually polycyclic. But these are the numbers of electrons that are delocalized in the ring that will yield aromaticity. So with that in mind, let's take a look at these. So here's this first one. We've got the cyclopentadienyl anion. So it's a cyclopentadiene, but it's an anion. One of the carbons has a formal negative charge. So is this aromatic? Is it cyclic? Yes, it is cyclic. Is it fully planar? It is fully planar. Now, this one's actually tricky because a lot of students would say, now, wait a minute, Dave, this is not fully planar because we've got an sp3 carbon here, right? That's an sp3 carbon. However, we have to consider the composite resonance structure. The composite resonance structure looks like this because that negative charge is delocalized. It's shared around every single carbon in the ring, because we can draw, right? We can put this negative charge here and then push this over there, and then we could push that up there, right? And so now all of a sudden we'd have a double bond there and a double bond there and a negative charge there, and we could do that we could do that 5 times, right? So we could have 5 different resonance structures. So when you look at the composite, you can see that they're all almost entirely sp2. So they're sp2 with a tiny bit of sp3 character, but essentially it is fully planar. So it is cyclic, it is fully planar, it is fully conjugated, right? We can push this pi electron density all around the ring. And now lastly, does it satisfy Huckel's rule? We have 6 pi electrons, because there are 2 in each pi bond and 2 in a lone pair. 2 plus 2 plus 2 is 6. So yes, we do we satisfy all of the criteria, and this one is aromatic. Now going on to this one here, we have this 1, 2, 3, 4, 5, 6, 7-membered ring. We have a 7-member. It's a cycloheptatriene. It's a cycloheptatriene, and the 3 pi bonds are conjugated. However, what do we notice here? This one does not have any pi electron density. So we have to understand that it is cyclic, and there is some conjugation, but it's not fully conjugated. There is no resonance structure. There's no resonance structure that will yield any pi electron density on this carbon. Therefore, it does not qualify, even though it satisfies Huckel's rule, right? There are 6 pi electrons. We don't even care about Huckel's rule because we're establishing prior to that that it's not fully conjugated. So now here's the important thing that we need to understand. This is non-aromatic. Let me do that in pink because I did the other one in pink. Non-aromatic. And that needs to be distinguished from anti-aromatic in the following way. Anti-aromatic is something that satisfies the first 3 criteria for aromaticity. It is cyclic, it is fully planar, it is fully conjugated, but the number of pi electrons is actually 4n instead of 4n plus 2. So that would be like 4, 8, 12, all the ones in between here, right? In between 2 and 6 is 4. In between 6 and 10 is 8. In between 10 and 14 is 12. So all the multiples of 4, basically. So if it looks like if it satisfies everything, all the criteria for aromaticity, except the number of pi electrons follows 4n instead of 4n plus 2, that would be anti-aromatic. It's specifically a destabilizing situation. And in fact, cyclooctatetraene adopts a puckered tub shape because it's actually more energetically favorable than being fully planar and achieving anti-aromaticity. So aromaticity is a stabilizing situation. It brings the molecule to a lower energy. Anti-aromaticity is a destabilizing situation for various quantum mechanical reasons that we don't need to get into. So aromatic, non-aromatic. Now let's look at this one here. This is a pyrrole, and pyrrole has, so is it cyclic? Yes, it is. Is it fully planar? It is. And then for the same logic here as with the cyclopentadienyl anion, you would be telling me, hey, but Dave, that nitrogen is sp3 hybridized, right? So that's tetrahedral. That's not planar, but we have a lone pair here. What happens if you start drawing resonance structures, right? You could put an anion on there. You could push it the other way. So when you look at the composite resonance structure, you realize that it is fully planar and it is fully conjugated. That pi electron density is going all the way around the ring, and it is 2, 4, 6. We have 2 from each pi bond, and then 2 from the lone pair. That's 6 pi electrons. So this one is aromatic. So it's actually extremely similar to the cyclopentadienyl anion. It's just that instead of C minus, we have N with a lone pair. So really the same logic on all of the above. So it's very important to understand that set of criteria here to establish aromaticity. Cyclic, fully planar, fully conjugated, satisfies Huckel's rule. And then we want to be able to distinguish between aromatic and then also between anti-aromatic and non-aromatic, because many students at first confuse the two, as well you might, right? Because anti-aromatic, non-aromatic, they both sound like the same version of not aromatic, but they actually mean slightly different things. And anti-aromatic specifically means that the number of pi electrons satisfies 4n rather than Huckel's rule 4n plus 2. So that's aromatic, non-aromatic, aromatic. Okay, let's see if I missed anything. The Golden Geek, yes, I do love bagels quite a bit, actually. I'm a big bagel guy. Okay. So moving on here, we need to periodically review some of the reactions that we've already gone over. So we spent a lot of time with Grignard. So let's review some Grignard. Let's make sure we remember how to do these. So we have this ester substrate, and then we have an excess of ethyl Grignard reagent in diethyl ether. So the ethyl Grignard reagent looks like this. So what do Grignard reagents do? Grignard reagents attack carbonyls, right? We know that. And that's because, remember, this carbon right here is partial minus This is an example of Ompelung chemistry. We have, it's an inversion of polarity. So when we have the alkyl bromide, the carbon that bears the bromine is partial plus because of the polarity of that bond. But then when magnesium inserts itself into that carbon-bromine bond, it inverts the polarity of that bond. Now, all of a sudden, carbon finds itself more electronegative than magnesium. So now it is partial minus. So Grignard reagents are a source of nucleophilic carbon. That's what a Grignard reagent is. And nucleophiles will attack carbonyl carbons. Remember, carbonyl carbons are electron deficient. The electron density in that carbonyl is being pulled towards the more electronegative oxygen atom. That leaves the carbonyl carbon electron deficient, partial plus. So partial minus meets partial plus. That's the name of the game. So let's push that up here. Let's have that attack carbonyl carbon. Push the pi bond up there. We don't have a lot of room here, so I'm just going to skip a step. I'm going to have that come back down, reform the carbonyl, kick off this methoxy group. Okay, so we're going to end up with this, the butanone. So this right here is the new ethyl group, right? This ethyl group is from the ethyl Grignard reagent, right? And then to be thorough, we will say plus CH3O minus, right? That left too. So now what are we going to do? We know, first of all, it said that we have excess ethyl Grignard reagent. That's important because when we do Grignard on an ester substrate, we can add 2 equivalents of the Grignard reagent. We can't add 2 different ones. We don't have that level of control. Whatever's in solution, any Grignard reagent will attack. So if you have more than one Grignard reagent in there, it's impossible to control what happens. But if you want to add 2 equivalents of the same alkyl fragment, this is an excellent strategy because Grignard reagents attack carbonyls. And when the first Grignard reagent attacks the ester, you're reforming the carbonyl. When the alkoxy gets kicked off, we've reformed the carbonyl. Here's butanone. And we have more Grignard, we have more ethyl Grignard reagent in there, right? It's at excess. So we've got more of that. It's still in solution, swimming around, sees the ketone, and it's going to attack. So let's get another one on there. Let's do this. So you could have drawn this a different way, but now we have this, right? We have got that ethyl group, and now this one are the 2 ethyl groups that came from the 2 ethyl Grignard reagents. And then this methyl right here is this methyl right here. That got pushed back when the other one attacked. You also could have left the methyl there and put an ethyl on the dash bond or wedge bond, right? You can draw it different ways. It's fine. I like to draw it this way. I just like to have the longest carbon chain in the plane of the page. That's just how I like to do it. And then we have aqueous acidic workup. So the Grignard is done. The reaction is done in the flask. We're going to toss in some ammonium chloride or something to quench the reaction. And all that means is we've got oxyanions in solution. We want to neutralize them. So we need a pretty soft source of protons like the ammonium ion. And that will give us our product, which is going to be this. We've got 3-methyl, 3-pentanol, and we do not have any other stereoisomers because of the symmetry of the molecule. 2 identical ethyl groups. That's the one. That's all we get. So once again, Grignard reagents are sources of nucleophilic carbon. They tend to attack. They can attack other things, but usually we're attacking carbonyl. We're attacking carbonyls, be they aldehydes, esters, aldehydes or ketones, or esters. When we have an ester substrate, we have the opportunity to attach 2 of the same alkyl fragment via 2 identical Grignard reagents. So we have this methyl, and then and that's still there, and then we tacked on 2 ethyl groups. So that's Grignard. That's that. Okay, let's see what I missed. Here. Speed Tumbler says, is there an example where you have a lone pair but can't draw a bunch of resonance structures? Certainly, if there's no conjugation, so like pyrrole, if you took away the pi bonds, right, now you just have that cyclic amine. There's no resonance here, right? Where's the lone pair going to go? Nowhere. It has nowhere to go. That lone pair is localized exclusively on that nitrogen. There's no resonance. So sure, good question. Citizen CJ says, how often do you do these? I do these every Tuesday at 5 p.m. Pacific time. Every week. HH says, remove the chirality from that alcohol. There's not meant to be a chiral center. I have not drawn a chiral center, right? I'm just showing the accurate geometry of the molecule. You do have to show the tetrahedral geometry at that center there, right? That is sp3 hybridized tetrahedral, 109.5 degree bond angles. That doesn't mean it's chiral, and you're correct that it is not chiral. Cool. Okay. Moving on. Which of the following reactions will proceed with a greater rate of reaction? So these are two electrophilic aromatic substitution reactions. So first of all, let's go ahead and draw the products, right? What are we going to get? We have aniline. So aniline is aminobenzene. And we're going to do chlorination, right? Cl2 with iron trichloride catalyst. These are the conditions for chlorination. And we know that that an amino group is an electron donating group. Therefore, it is an orthopara directing group. So we are going to get two products. We're going to get the ortho product. Whoops, not NH3, NH2. And we're going to get the ortho product. And the para product. So there's your ortho, there's your para. And once again, that is because this is ortho-para directing. And almost all ortho-para directors, right, the exception would be the halogens, ortho-para directors tend to be activating. Right, because they're donating electron density into the ring. When you have the rhenium ion intermediate, you have a positive charge in the ring. And so if there's a lone pair on that substituent that's donating pi electron density into the ring, that is stabilizing that rhenium ion intermediate. And so the intermediate, the generation of the intermediate is the slow step because you're generating the least stable thing. Right, we went from something neutral to something with a formal positive charge, so we're going up in energy, right? So if you're going up in energy, the more stabilized that intermediate is, the lower that sits on the energy diagram, the lower the activation energy is, right? The less kinetic energy is required to get that first step to go, to get that rate determining step to go. So activating, so the electron donating groups are activating, and almost always orthopara there, or no, actually, yeah, all the donating ones are orthopara. The halogens are withdrawing, but also orthopara. So now let's look over here. We've got nitrobenzene, and we're going to do a bromination. So it's the same. It's right, chlorination, bromination, exact same conditions. We just swapped out every chlorine atom is a bromine atom now. And we know that this guy is a meta-director, right? The nitro group is electron withdrawing, right? It's electron withdrawing because it's got a positive charge on that nitrogen atom, right? So if we have a positively charged nitrogen, that's going to be withdrawing electron density from the ring in an effort to stabilize the positively charged nitrogen atom. So if you have a positive charge on the rhenium ion intermediate, that's going to even further destabilize that intermediate. You're withdrawing electron density away from a positively charged species. That's going to be further destabilizing. And so that is going to be deactivating. And what are we going to get? If it's a meta director, whoops, get this color. If it is a meta director, it is going to direct incoming electrophiles to the meta position. So there's our product there. That is going to be meta substitution. So we definitely want to know the products we're going to get, but this says which one is going to have a greater rate of reaction. And so it's going to be the activating one, right? Because the activating one it brings the intermediate to a lower energy. Therefore, the activation energy to get to that intermediate is lower. When you're talking about rate of reaction, you're always looking at the activation energy, right? Because the activation energy dictates how much energy is required in a collision to get the reaction to go. And the higher that activation energy is, the lower the proportion of molecules that will collide with sufficient energy to get the reaction to go, right? Imagine you're trying to roll a ball over a hill, right? If you're trying to roll a ball over a hill like this one, you no matter how wimpily you throw it, right? If you roll the ball over this tiny little hill, you really don't have to roll it that hard. So almost every single time, even if you just go like that, or almost every single time, you're going to get over that hill, right? But what if you've got this huge hill? Now you're really going to have to roll that one hard, and you have to roll it so hard that 9 times out of 10, even though you rolled it your hardest, you can't get it over, right? And so what that means on a macroscopic level, if we're saying that we have a reaction that is trying to happen and only 10% of the collisions result in a successful reaction versus 95% of the collisions resulting in a successful reaction. On the macroscopic scale, what we see that as is going faster or slower, right? 1 in 10 collisions makes the reaction go. It's going to go slow because there's so many quadrillions and quintillions of molecules that have to react. Almost all the collisions make the reaction go. It's going to go really fast because every time it collides, it goes, right? So that's the connection that we need to understand kinetically between the molecular level and the collisions and the activation energy versus the macroscopic level, which would be rate, right? That's just we're watching to see how long it takes the reaction to go. So greater rate of reaction, that would be this one. The one with the activating group, the one with the electron donating group is the activating group, stabilizes the intermediate, makes the reaction go faster. Okay, what did I miss? Okay, great. So Jack Brown says, in brief, what makes activators orthopara-directing? So let's say we have NH2. Okay, so and so let's say we're going to react with some electrophile, and we're going to get, let's say we have, let's say we get ortho substitution. So that will leave the positive charge there versus meta substitution. Stop. So E is just any electrophile. We don't care, right? And so there's that. There's NH2. That would leave the plus charge there and another pi bond there. So what do we notice here, right? This nitrogen atom has a lone pair. So let's put this lone pair right there. Oh, let me do red. Let's put this lone pair right there. We can draw another resonance structure. That pulls the positive charge up to the nitrogen atom. So what we're saying is that when we have, the para substitution yields the same resonance structures as ortho substitution. So what we're saying is if we have ortho substitution, so some electrophile, doesn't matter what, went to the ortho position, that left a positive charge there. Or if we could draw two other resonance structures, right? We could push this pi bond there and get the positive charge here, and then push this pi bond here and get the positive charge here. So when you have ortho, and then with para substitution, it'd be the same. So ortho or para substitution puts the positive charge in the intermediate in these three positions. And if it is in these three positions, one of those positions is immediately adjacent to the electron donating group, which we saw here by resonance. That nitrogen atom can donate the lone pair onto that carbon and stabilize it. Right. So this is a state. Anytime you are further delocalizing a charge, you're stabilizing the charge. So you're adding another resonance structure to the set of resonance structures, and you're stabilizing that positive charge. So this intermediate is lower in energy than if the amino group were not there, right? If the amino group simply were not there and we were doing this EAS reaction on benzene, on unsubstituted benzene, the intermediate would be higher in energy than this one. The fact that the amino group is there, it is stabilizing that iridium ion intermediate. It's bringing it to a lower energy by donating electron density into the ring that bears the formal positive charge. And what we especially need to understand is that that only happens when the substitution is ortho or para. When substitution is ortho or para, the positive charge is in these three locations, in the three resonance structures for the intermediate. If we do meta substitution, the positive charge is only here or here or here. It will never be in that position that is adjacent to the substituent, right? So meta substitution almost never happens because the intermediate is at a higher energy than the ortho-para pathway. The ortho-para pathway has a lower energy intermediate because it's being stabilized by the adjacent electron donating group. Conversely, meta directors go meta not because they're stabilizing any intermediate, but instead, imagine NH2 here is NO2. NO2, you'd have a positively charged nitrogen adjacent to a positively charged carbon. That's extremely unfavorable, right? You don't want adjacent positive charges. They're further destabilizing one another, right? So meta directors go meta, not because it's a stabilizing pathway, but because it's the least destabilizing pathway. If you go if you have a meta director, NO2 here, and the positive charge is never adjacent to the NO2, that's the best situation you can have, right? It's the best pathway available. So electron withdrawing groups are meta directors because it avoids this specifically least energetically favorable possibility, right? So it makes it even worse by the presence of that substituent. So the rates of reaction here, the activating group would be the fastest. Unsubstituted benzene would be next. Then nitrobenzene is the slowest because it's even worse. The presence of the NO2 group makes it worse, makes the intermediate even higher energy. So I hope that helps. I do have a tutorial that explains all of that with all of the resonance structures drawn. That if that was confusing, check that one out. Iraq Lee. So that's that's what I said. What determines if it is an ortho, meta, or para director? So if it is electron donating, it's going to be an ortho para director for this precise reason, right? Because you have an electron donating group that is stabilizing the adjacent cation in the ring. Which brings the energy of the intermediate down. So that lowers the activation energy. That's favorable. Once again, the only exception is halogens, which are electron withdrawing by virtue of the polarity of the bond, but orthopara directing because of the ability to put a lone pair in by resonance. So that's the one that you have to memorize. Yeah. Okay, so that's it. Caught up. All right, let me just erase some of this because we need some room here. Oh, I'll erase just this. Okay. So draw the potential crossed aldol product. So enolate chemistry is very important. There's a lot of different kinds of enolate chemistry. The first one we usually learn is aldol condensation. Usually start with a very simple one, one compound doing aldol on itself, but you can also have a crossed aldol product. So draw the singular potential crossed aldol product. So sometimes when you have two carbonyl containing compounds, like say an aldehyde and a ketone, there are two potential crossed aldol products. You can have the aldehyde attacking the ketone, and you can have the ketone attacking the aldehyde. Here we've got two aldehydes, but there's only one potential crossed aldol product. Why is that? Let's see if we can figure out why. So we've got sodium hydroxide. Where is it? Here we go. So we've got hydroxide. Which proton is it going to get? Remember, it is the protons on the carbon that are alpha to the carbonyl that are mildly acidic, right around pKa 19. So where do we have protons that are in the alpha position? Well, we've got two right here. So these guys are around pKa 19 because of the situation where the resulting anion would be conjugated with a carbonyl. Benzaldehyde does not have that. Benzaldehyde does not have any alpha protons, right? Here's the alpha position. This carbon has 4 bonds to other carbon. There are to other carbon atoms. There are no implied hydrogens here. This carbon does not have any hydrogen atoms. So there are no alpha protons. So we can't do it. So we can only enolize the aldehyde or the propanol. We're going to enolize the propanol, get that proton, push that up there, push that up there. And so save some space. Let's go all the way over here. We're going to get this enolate, right? We got the pi bond there and then the oxyanion there. So now this could admittedly attack another equivalent of propanol, but it's asking, it wants the potential crossed aldol product, right? We specifically want to get the crossed aldol product. So in reality, you're going to get a mixture, right? Enolate chemistry can be very messy because everything's attacking everything. But for the purposes of this question, what is the potential crossed aldol product? So let's react this with benzaldehyde. So that's going to come back down and reform the carbonyl. This pi bond is going to go over here and then kick that up there. Okay, we have to be very deliberate with these arrows. This one goes from the negative charge to the center of the CO bond, indicating that we're reforming a pi bond there. This arrow goes from the center of that pi bond, indicating that the pi bond is attacking that carbonyl carbon. So it ends right on the carbonyl carbon. This arrow goes from the center of that pi bond in the carbonyl and lands on the oxygen, indicating that those electrons remain with the oxygen to form an oxyanion. So what does that end up looking like? So the carbonyl is reformed. Now here's the tricky part. This carbon right here is acting as the nucleophile. This carbon right here is acting as the nucleophile, but there's another carbon there, right? There's one more. So we don't want to lose that one. Very important. Make sure that that carbon is still there. But here is the new bond. Here is the new bond there. So this one, this is the carbon-carbon bond we just formed. So this is the crucial part. This is the most important part. And this is where students most often get confused, right? And you can number the carbons if you need to, right? You can go ahead and go, hey, look at that. We got 1, 2, 3. Carbon 2 did the attacking, but carbon 3 is still there. Carbon 2 did the attacking, but carbon 3 is still there, right? So we've got that lonely methyl over there. But from carbon 2 attacked the carbonyl. So here's carbon 2. Here's what used to be the carbonyl carbon. Now it bears the oxyanion. That's where the new bond is. So make sure you didn't gain any carbons. Make sure you didn't lose any carbons. Go ahead and sit there and count all the carbon atoms if you have to, right? You got to make sure. So there's that. And then we have, we're an aqueous solution. So let's just go ahead and protonate that oxyanion. And we're going to get this. And then a little bit of heat here. What happens, because this is we're doing an aldol condensation. This is the aldol addition product. But when conditions are hot, we can go ahead and get the aldol condensation product. Condensation means we lose water, lose a water molecule. And we lose a water molecule in the sense that we lose a proton and a hydroxyl, not a literal water molecule, just combined. So let's go ahead and get this guy. This will form the pi bond there, and this will kick off hydroxyl. Now, a lot of students will say, but Dave, hydroxyl is a terrible leaving group. And you're right. However, we are in strongly basic conditions. When you're in strongly basic conditions, the hydroxide ion can be a leaving group because solution is full of hydroxide ions. If solution is full of hydroxide ions, one more is not going to hurt. So in strongly basic conditions, hydroxyl can be a leaving group. And that will give us our crossed aldol product with the pi bond there. So we lost H2O. We lost an H and an OH. This is the H and this is the OH, which together make H2O. So that's why it's condensation. So that's the product there. There is our crossed aldol product. You can very clearly see the fragment which came from where's the oops, not that. What's this? Where's my highlighter? Here we go. This is the fragment. This is the fragment that came from propanol. And this is the fragment that came from benzaldehyde. And this is gone, right? That oxygen atom is gone. That was lost in the condensation. So we made carbon-carbon bonds twice from the same location. It was this carbon 2 that made that first carbon-carbon sigma bond, and then it was that same carbon, the same two carbons formed a pi bond between them in the condensation step. So there's your aldol condensation. It's a crossed aldol in this case, and that's going to be our product there. Let's see what we missed. Nayla says, why is that one the one that attacks? If you mean the propanol, if the propanol enolizes and attacks because benzaldehyde is incapable of enolization. There is no alpha proton on benzaldehyde, so it can't enolize. It's impossible. So propanol will enolize and it will attack. It can attack itself. It can attack another equivalent of propanol, but it can attack benzaldehyde as well. Hopefully that is what you meant. Okay. All right, now we want to draw the mechanism for the following reaction. This is a Friedel-Crafts alkylation. So typically in an organic chemistry course, you are responsible for a certain number of mechanisms. You have to be able to draw the mechanism explicitly and accurately with all electron pushing arrows. And this would be probably a go-to for electrophilic aromatic substitution. If I was giving a test, this would probably be the one that I would pick for you to have to show the mechanism for. And so let's go over it. So when we are doing electrophilic aromatic substitution, we've got some aromatic compound, often benzene or a benzene derivative. We have some electrophile, and then we have some catalyst, right? The reason that we need the catalyst is that this reaction won't happen without it, right? The benzene ring is not going to do an SN2 on this carbon, right? If we had a good SN2 nucleophile, it could attack right here, kick off the chloro group, and we did SN2. But that's not how this one's going to go. So we need some catalytic complex to prompt the benzene to react. We need to create something that's so unstable that even benzene will react with it to bring the system to a lower energy overall. So here's the chlorine atom, right? Chlorine's got 3 lone pairs here. Excuse me. One of these chlorines is going to attack aluminum, right? Aluminum trichloride is a Lewis acid because, because we have partial minus, partial minus, partial minus, and partial plus, right? So remember, this is the Lewis definition. The Lewis definition is an electron pair acceptor. That's very different from the Bronsted-Lowry definition, where we're talking about proton transfer, right? In the Bronsted-Lowry definition, you can't be an acid unless something can't be an acid unless it has a proton. If it doesn't have any hydrogens, it can't be a Bronsted-Lowry acid. But something without protons can be a Lewis acid if it has an atom that is electron deficient, that electron density can coordinate to. So the aluminum atom is electron deficient, and a lone pair from the chlorine is going to attack, and that is going to generate this intermediate here. So we have boom, 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 Al, and then 3 more of these. And so what are the charges here? We've got a formal positive charge on the chlorine, right? Because chlorine is now showing 6 electrons in this Lewis dot structure. It's got 2 lone pairs. So 2 lone pairs and then 1 per covalent bond. 6 electrons is 1 less than its typical valence of 7, right? Halogens have 7 valence electrons. So when they're showing 7 in a Lewis dot structure, they're neutral. Here, it's showing 6. So there's a formal positive charge. And then this guy here, the aluminum, now has a formal negative charge, right? Because its aluminum has 3 valence electrons. Now it's showing 4. It gained an electron from chlorine. Chlorine gave it an electron, right? The 2 electrons in this bond used to belong exclusively to chlorine. Now they're in a covalent bond, so we count it as 1 for chlorine, 1 for aluminum. So aluminum gained an electron. That's got a formal negative charge. So what's going to happen here, in an attempt to neutralize this chlorine, this carbon-chlorine bond will break. Okay, and that is going to give us this this alkyl cation, and then AlCl4, which still has a formal negative charge, by the way. The aluminum atom still has a formal negative charge. So this carbon-chlorine bond breaks. These electrons go to the chlorine to neutralize it, but we're left with a carbocation. So this is why this catalyzes this alkylation, because benzene is not going to react with the alkyl chloride. It's too stable. But the secondary carbocation is so unstable that benzene will react with it. So now we've got benzene, and we've got this cation here. So let's go ahead and attack, right? That pi bond is going to go and attack. So we've got, let's say it went like this, and now we've got a plus charge there. So that pi bond went like that, grabbed that alkyl fragment. So this top carbon didn't lose any bonds because it was in that pi bond and it lost that pi bond, but now it's got another sigma bond to that fragment. But this one right here, this one lost a bond because it was participating in that pi bond, and then that pi bond left. So we've got a cation there. And now we've got, remember, we've got AlCl4, and we still have a negative charge here on the aluminum. Put that right there. So what's going to happen here is this, everything wants to neutralize. So what if we take, let's draw it this way just to be very specific. What if the electrons in this bond leave with chlorine, and then this chlorine grabs that proton, and then boom. Okay, and so what do we end up with? We have our isopropyl benzene, we have HCl, and we have regenerated our aluminum trichloride catalyst, right? So that's an important distinction, right? With a catalyst, catalysts are not used up stoichiometrically in the reaction. So it's going to participate, right? Aluminum trichloride interacts with the electrophile to generate the catalytic complex, and then the cation, the cation, the fragment that interacts with benzene. But then at the end of the reaction, this chlorine leaves, and we get our catalyst back. So then it's going to go and facilitate another reaction, and then another, and then another, and then another. That's what a catalyst does. It lowers the activation energy of a reaction, but it is also not used up stoichiometrically. So a small amount can facilitate hundreds or thousands or millions of reactions or whatever. So that's the mechanism. Let's just go over it one more time. The chlorine is going to attack the aluminum atom because it's electron deficient. We get this complex here. The electrons in this carbon-chlorine bond go to the chlorine to neutralize it, yielding the secondary carbocation and AlCl4 with the negative charge on the aluminum. Now we have a carbocation. Benzene can react with that. Pi bond goes and grabs the cation. That's going to put the isopropyl group on there, but it leaves a positive charge, right? This is a typical EAS, right? We've got our rhenium ion intermediate. We could draw 3 resonance structures for that if we wanted to. We don't have to right now. You could, but so there's that. And then this complex is going to come back and restore aromaticity. So the electrons in this chlorine aluminum bond go to chlorine so that aluminum can be neutralized, right? If aluminum loses this electron, it'll be neutral again. So that's good. And so these go to chlorine, and then a lone pair on chlorine grabs this proton to form HCl. The electrons in the carbon-hydrogen bond go to form the carbon-carbon pi bond, thus neutralizing the positive charge in the ring and restoring aromaticity. So that gives us isopropyl benzene, HCl, and aluminum trichloride catalyst is restored. So that's the full mechanism. That would be full credit on a test, and that's it. Let's see. Pagan Beef says, are all carbon-carbon bond lengths identical? No. So certainly they differ if it's a single, double, or triple bond, right? The more bonds between them, the bond length contracts. Triple bond is the shortest, then double bond, then single bond. Falak says, could you please share tips on learning organic chemistry reactions? There's no secret, right? The only thing I would say is, well, there's a couple of things I would say. Number one is just do as much practice as possible, right? Do practice problems, do the practice quizzes. Make sure you're not just memorizing structures. Make sure you're understanding what is going on mechanistically. What is attacking what, why, where's the electron excess, where's the electron deficiency? Can you replicate that on any substrate, right? Not just the one in the example. You have to be able to do that for any substrate that's given to you. And then number two, sometimes you do need to do flashcards. I would say flashcards are good simply for memorizing the reaction conditions. So you want to memorize, okay, these are the conditions for hydroboration oxidation, right? You have to memorize that. These are the conditions for ozonolysis, and then what that does, right? So if you memorize that, then you can apply that to any substrate that you're given. Jan asks, is this Friedel-Crafts alkylation? Yes, that's correct. It is Friedel-Crafts alkylation. That's exactly what it is. The Oriorit says, is this boat or chair conformation? Neither. So benzene is fully planar. You're thinking of cyclohexane. Cyclohexane will tend to adopt a chair conformation, but not if it's benzene, right? These these are all sp2 carbons. These are all sp2 carbons, 120-degree bond angles, trigonal planar. Benzene is flat. Benzene is flat like a piece of paper. It's like this, and then all the hydrogens are, even the carbon hydrogen bonds are in the same plane as the benzene ring. Totally flat molecule. Pagan Beef, all carbon bond lengths are identical, and this equivalency can be exploited by catalyst forms. Not sure what that means, but yes, I mean all carbon hydrogen all carbon bonds. Sure, if all bonds are if a particular type of bond is identical in every instantiation of that bond, then it looks identical to whatever catalyst it's reacting with. Sure. Fire King asks about proton NMR and carbon 13 NMR. I'll try to find a carbon 13 NMR. I did have two more proton NMRs on this sheet. So obviously we'll pick up here next time and we'll do some more NMR. I'll try to remember to put a carbon-13 NMR on there, or even better yet, conjunction C13 and proton to figure it out. Okay, so yeah, that's the time today. So once again, please check out the QR code on the top left if you want to see what other types of office hours Chegg is offering in different courses, so you can have help all semester long, all classes you're taking. Otherwise, I'll be back again with Chegg next Tuesday for the next 6 or 7 Tuesdays, I believe, at 5 p.m. Pacific time. Just like this week, we'll be going over more Organic Chemistry 1